A very good afternoon to all of you. I'm Ankita from nasscom. I know we all are at home being responsible and staying safe indoors, and I think one of the best option nowadays for utilizing and optimizing our time is to reskill ourselves, upgrade ourselves. And we at nasscom Product Council are always there coming up with something exciting to learn with great speakers and on great subjects. Today is a special day as we will begin our next data science series after successfully completing the previous ones with 10 amazing episodes. To initiate the first episode, I have with me Vikas Agarwal, who is a senior principal data scientist at Oracle. So stay tuned and listen to him. And before I hand over to Vikas, two more things from my side. Please ask questions anytime during the session. Vikas will cater to them at the end. Also, please leave your valuable feedback post the session to help me improve my future episodes. Welcome, Vikas, and over to you.
Thank you, Ankita. Good afternoon and welcome everybody. Today we're going to talk about how when we use AI to solve problems in the enterprise, how is that different from solving a game like chess or Go, or like an ImageNet challenge, which is academic, or a Kaggle challenge. Some Kaggle challenges are becoming more like enterprises challenges now, or Moonshots, like from Google X and so forth. So my email address is down there, vikas.a.agrawal@oracle.com. So if you have any questions, you can send me over there. Of course, we'll answer questions now. So we'll get started right away. First of all, we'll redefine intelligence or artificial intelligence compared to what has been in the textbooks for a while. Now, human intelligence, most of us kind of understand. It is intended to find the most efficient way to realize human goals. And what that means usually is one is able to discriminate between what paths to take this way or that way, which are positive or negative in our progressing towards the goals we have chosen. Now, as you know, if we don't specify a goal or it's not properly specified, then any path will take you there. So that's what the Cheshire Cat told Alice, right? Alice asks the cat, which road do I take in Alice in Wonderland? And the cat asks, where do you want to go? And Alice says, well, I don't know. So then the cat said, it doesn't matter, meaning which path you take doesn't matter. Now, I will not go through this paraphrase of Alan Turing's test, which is that human action without a higher goal or internal purpose beyond just survival will appear indistinguishable from sophisticated automatons for human actors. So now we'll come back to this when we talk about creating artificially intelligent systems. Now, the old definition of machine intelligence in textbooks like that of Stuart Russell and Peter Norvig is find the most efficient way to realize machine goals rather than human goals, which of course the machine goals could be pre-assigned by humans. And those machines will continue executing those goals, even if it contradicts human goals, which may have now changed. The new definition of machine intelligence coming from Dr. Stuart Russell's lab is, we find the most efficient way to help humans realize uncertain human goals, as in the human goals may change. And the machine will keep checking if the goal has changed. So this is a very important thing to keep in mind. And therefore, we need to create systems which can amplify humans in the enterprise rather than replace humans in the enterprise. So I'll show an example of a system like this, where you have data coming in from RDBMSs like Oracle's, GraphDBs, triple stores. Information is extracted from text, video, audio. There's sensor data coming in from Internet of Things, and we do digital signal processing and so forth. And for all of these, we provide a natural interface with touch, speech, language, and vision. Now, most of you would be familiar with these, and the techniques used and the technologies used. I'll not go through all of that detail because most of you might be familiar with these, and perhaps many of you know this much better than I do. Now, the key thing to note here is at the leaf nodes, this is a whole network, and at the leaf nodes, There are high quality, perhaps deep learning models in computer vision and natural language processing, speech recognition, and those act as, some of them are hardware sensors, some of them are software sensors. And all of those signals need to be integrated at multiple levels of hierarchy. And at some point, one needs to understand what causes what to be able to make reasoning and decisions that go to the level of the humans. And to do that, one needs to be able to create hypotheses, do what if analysis, seek predictions and explanations, make informed decisions. Now, we will go through this step by step very carefully with 3 specific use cases and see how you can build on this. So now what we usually consider machine learning use cases are usually multi-year moonshots funded by tech giants like internet scale media interpretation, like image identification, language translation, or self-driving cars. Usually they have large volume of labeled training data. Now, the challenge in this is that you can often be confident that the training set effectively represent the full distribution of observations seen in production. Now, this often is violated in industry, in enterprise. Now, the machine learning training time and or cost is not a strong constraint. Often there's a big network of GPUs, TPUs available. And the goal is often to provide fully automated decision making. Often they use custom or novel algorithms developed by dedicated teams of world-leading machine learning researchers. Now, look at what happens and what's needed in the enterprise. Enterprise use cases look very different. There may be limited training data. It may be a mix of labeled and unlabeled data. It may not be initially clear if the training data represents the full distribution of what we'll see in production. And this, you will see later, will become very, very important in how we create our machine learning and AI systems. Often we need to apply a combination of techniques to solve the problems. We have cost constraints, time constraints, resource constraints, unlike moonshots. We often need a decision support system, like I mentioned, augmenting humans rather than fully automated decision making. But you may say, wait a minute, I have solved that game of chess, I've solved the game of Go, I've solved some video games also. What is this little enterprise problem? What can it, I can solve it just like that. Well, the challenge with enterprise problems is often the problem that you have to solve is not well formulated. So games are fully formulated, as in the full game, exactly what the problem is and what the goal is. But with enterprises, it may not be very clear. And to make the goal clear, the problem clear, it requires careful science of the domain. So this deep domain expertise makes a difference between a toy system versus a in production high value system. Even if you have a problem statement, often the goal is not clear. It has to be determined, carefully specified. And often the questions that model need to answer are counterfactual, as in you may have data on X caused Y, but the question you may want to ask is, what if X did not happen? Then what happens? So we need causal models for that. Now in the games, the other thing that happens is that, okay, the problem is well formulated, goal is clear. The other thing that happens in games is that the rules of the game, which are relationships between things, and the board, often these are board games, the causal domain knowledge, it's very well known. In the enterprise, the rules of the game might be changing or may not be fully known, or they may not be well represented in computers. And the other problem with trying to take game-like systems and use it for the enterprises, in games you can play against yourself and learn, but in enterprises you can't play against yourself. It's too risky. You'll destroy yourself. And the other thing we need to note is that the data that you generate when you play the game against yourself or against humans, the data generation is dependent only on the computation, whereas in the enterprise, the data generation depends on the underlying process, the environment, the stimuli. Then there are further challenges. One is that there's no direct feedback. Like on Kaggle, There is no leaderboard. You are your own leader. You have to figure out what is success. Data is not often predetermined. Like on Kaggle, the data may be given. The data is already cleaned or may not be cleaned, but it's just in one place. So it may not be pre-collected. You clean it basically. So you may start off being a data scientist or calling yourself a data scientist, but you start off really as a data janitor. Just a minute. Yeah. And data often cannot be generated on demand, as happens, for example, in games. And data changes. This is a very big challenge. Let's say on Kaggle, what happens is your test set is fixed. Your training set is also fixed. Now, in the real world, the test set is dynamic. Your training set is dynamic. So you have to keep testing, refactoring, Big challenge. So these are structural challenges. Operationally, what's different in enterprises is the models need to work with people. Not everyone can or should see recommendation because there may be liability. We'll come to this remember this one. We'll come to this in the first use case we'll see. Also, not everybody, especially decision makers, may not like to see your output. You may show all kinds of numbers, but often they are looking for output in terms of vitamin M, as in money. So how you present the material is very, very critical. Then there are issues of behavioral psychology. The interventions and analysis is often driven by irrational choices, and people find a way around KPIs, surveys, and sensors. So our systems need to take this into account when we deploy them and even when we create them. And this also takes care of issues like biases and so forth. Then, as we discussed before, there are constraints in the solution complexity, in response time, memory, compute. All of these matter. And the last one here is engineering and scalability can kill you. The issues of model deployment, end-to-end, performance monitoring, control and update, logging. And also, I mentioned the leaf level nodes, the computer vision and speech and so forth. Those nodes must be very reliable with traceability, explainability, and provenance in all the data products we create there. And what we're seeing is more and more we are able to create integrative AI models, and these are better and better at actionable intelligence. Now, if people in the enterprise ignore the advice, that could be irresponsible, reckless, or even discriminatory. Who is to blame if the advice given by the AI system is erroneous, or if it's right and it's disregarded? Now, decisions are supposed to be driven by identifying causes, but in reality, they are often done by politics and turfs and highest paid person's opinion. So to change that, to make sure that decisions are driven by identifying causes of problems, we need to encode causal domain knowledge and make sure that that is communicated to the decision makers. So let's look at causality and this issue, and along the way address each of these differences between enterprise and games. So we'll see what it takes to create machine learning systems for the ordinary enterprise. Now, if you go to the textbook or you take an online course or a university course in machine learning or AI, you'll be told this story. You have training data, you have test data, you have a learning algorithm, you create a model, and from that you get predictions for the runtime, and you're done. Now, the reality looks a lot more rich, because just getting your data, you may need legal approvals. You may not have data, you may have to get annotations through crowdsourcing. You may need to actually extract the features, understand it based on the domain. You may need to do some active learning to figure out which areas of the data are deficient. And then you may have to go through many models to figure out which model works best. You may need to explain the model. You may need to do error analysis. You may need to get customer feedback to fix the problems, etc. Now, this is just for one model. In the real world, what happens is real world enterprise systems may have 200, 300 models working together. Right? Now, to integrate all of those is another fun problem. Now, notice this is just one model. Now, even with this one model, you need So notice all that one model is in that ML code in the center in this slide. This is a slide from Google. It was published in 2015. So you still have the issues of configuration, data collection, data verification, feature extraction, process management, machine resource management. So you don't just need data scientists, you need data engineers, you need architects, you need policy makers. All of that has to happen. The infrastructure team, the DevOps team, all of that has to happen to create these enterprise systems. And this is all assuming you have purely data-driven systems, which a lot of people say, well, you know, what's wrong if I just throw all my data at some set of functions and find some nuggets serendipitously? I get this question very, very often, that, you know, why do you have to do this science so carefully? What's wrong with this? Well, if you are in this school that, you know, I have a lot of data, I'm going to throw it at some algorithms, see what I get. Well, if you have that kind of money lying around, let us talk. Send me an email. But even for very well directed, carefully designed systems that are purely data driven, there exist problems, because the models may not capture the underlying data generating process, even while it faithfully mimics the IO. The input output may be correct, but the data generating process is not modeled. And the data generating process is basically the rules of the game, which you don't know in the enterprise. In the chess or Go, you know the rules, but in the enterprise, you don't know. So these rules of the games can tell us what could have been. See, we see the data of what was, but what could have been, we haven't seen it. It's not observed. So to get at that, you need to model a data generating process. Now, because of that, the models are brittle outside the data boundary conditions. As soon as your input data is outside the training data, you suddenly find that your model doesn't work anymore. And your model tries to fit the new data into the old distribution, and it doesn't work so well. And obviously, you're not able to answer causal questions, counterfactual questions. You don't believe me? Okay, let me give you some evidence. There's three kinds of brittleness in these purely data-driven systems. One is out of distribution, which I mentioned, with no perturbation, no adversarial input, just out of distribution. Now, also, there might be some adversarial input small enough that humans will find the image, speech, data as normal, but for machines, it is beyond the decision boundary. And the perturbation is large enough that no humans would consider the sample to be in the class, yet the machine finds it within the class. So first example. Now, Dr. Jeffrey Hinton, who has pioneered quite a bit of advances in deep learning, he said in 2017, if you work as a radiologist, you're like Wile E. Coyote that is already over the edge of the cliff but hasn't looked down yet. Now, his idea was that based on certain data that was showing that from 3 different hospitals, they collected data, and they said, you know what, we're able to do better than radiologists at reading X-rays. Well, what they found in a subsequent study, which had a lot more data from many more hospitals, it does not work across hospitals. It gets confused. It gets cheated inadvertently. For example, it focuses on things like that the image came from a portable X-ray machine, or there's a thing called a laterality marker, which is just a L essentially. Right now, a portable X-ray machine, the issue is that you use a portable X-ray machine if the patient is more sick. So if the X-ray came from a portable X-ray machine, you essentially label it as sick or as a tumor or something. Right? It got confused by machine or manufacturer specific signals, resolution specific issues, hospital specific issues, department specific issues. Right? Now, you wouldn't expect that. You would expect, well, this thing should be focusing on the actual tumor. It should be actually focusing on the lesion. So as soon as you take to a new hospital, from 96% precision, you come down to 70% precision. That's pretty bad. But of course, people are working on improving this. Then there are simple things, right? Like this one, right? Rotating the objects in the image confuses the convolutional neural networks. Now, this is not the case with capsule networks, but with convolutional neural networks, this is the case. Right? That you have the stop sign. Now, if you put it like this, now this is a side view of a dumbbell, the second one, the middle one. And on the right-hand side, if you take this oblique view, you get a tennis racket, perhaps. Or this one, the one below gets classified as a manhole cover, or this mushroom gets classified as a pretzel. So So Kevin Lyman, he's the CEO of the radiology startup Analytic. He has said AI will not replace radiologists, but radiologists using AI will replace those. So we can use it as assistive, augmenting humans. Second kind of brittleness is with some adversarial input, where the humans think this is normal, but machine thinks it's not normal. So, for example, this case, right? You take this image on the left-hand side, add the noise in the middle. It goes from a benign tumor to a malignant tumor. Or very interesting case of this text substitution. So if you say, instead of saying patient has history of back pain and chronic alcohol abuse, you just say patient has a history of lumbago and chronic alcohol dependence. Now suddenly opioid risk goes from high to low. And similarly, an adversarial coding in the medical records. So in the left-hand side, the claim was denied, and the right-hand side, the claim was approved. You just used fancier terms. Similarly, here, this was published in the journal Nature. So you look at the stop sign, you add a couple of these white and black rectangles, suddenly the machine thinks it's a speed limit, 45. So you keep going, you get a ticket, or worse, you get into an accident. Or here, the gentleman just wears this t-shirt and it doesn't even recognize that there is a human there. The third kind of perturbation is large enough that no human would consider it in the class, yet machine finds it within class. So here, the machine is just looking at textures. For example, in the first one, it thinks this is a penguin, but it's just a texture of a penguin. On the right-hand side, it's the texture of a starfish, but there is no starfish. So the issue is my model is going after wrong features or concepts or relationships. So, and that's why Jeffrey Hinton said convolutional neural networks are doomed. And look at this. So for example, here is this lady, right? The first one, the image is just straightforward and it classifies it as a person, right? Now the second one, you replace the eye and the lips, and suddenly it still thinks it's a person, which it is not. And in the third one, you just invert the original image. You didn't do anything. And here it thinks it's a coal black color. And here, it forgets, right? Is there a fix to this problem? Well, Judea Pearl, who got a Turing Award for Bayesian networks, said, you do domain adaptation, transfer learning, lifelong learning, explainable AI to solve this problem. But it requires a causal model of the environment. We'll talk about that. And it cannot be properly addressed at the level of association, at the level of correlations. And this is also the view of Yoshua Bengio. And this is a very important thing. And if this is one thing that you take away from this discussion, it would be this. The assumption that the test data is from the same distribution as the training data is too strong, which is the funny thing is every single course you will take is that's the assumption you make, that your test data has the same distribution as the training data. But this is often violated in practice, leading to very poor generalization out of distribution. So let's take a little bit relaxed assumption, which is that the test data was generated under the same causal dynamics, as in the system generating the data is the same, but inputs have changed, the initial conditions have changed. And that's a reasonable assumption. That's quite a reasonable assumption. Now, of course, the causal dynamics may also change over time, but that we can detect, we need to change the model. Now, so long as our machine learning models cheat by relying only on superficial regularities, such as the ones we saw thus far, which were brittle, they remain vulnerable to out of distribution examples, distributional shift, catastrophic forgetting, etc. So Joshua Bengio now is working on incorporating underlying causal relationships. You don't believe me? You still don't believe me? Okay. Look at the plot on the left. The plot on the left has exercise versus cholesterol versus exercise. Now, I have a little bit of a heavy frame, and you will notice on the figure on the right hand side, the figure on the right hand side basically tells me no need to exercise, because you know what, no matter what you do, you're actually the less you exercise, better your cholesterol is. But if you take age as a causal factor, which is not in the picture, but if you bring it in the picture as is on the left hand side, you will see that for every age group, 10 years, 20 years, 30 years, 40 years, 50 years, for each age group, the exercise makes a difference. The cholesterol is inversely proportional to exercise. So the question is, what questions can you ask? So typical causal questions is, how effective is a given treatment in preventing a disease? Was it the new change in price that caused our sales to go up, or there's something external going on? Or is it a marketing campaign? What annual healthcare costs can be attributed to obesity? Can hiring records prove an employer guilty of gender or racial discrimination? We'll talk about this specific use case today, and also about the disease one. I'm about to quit my job. Will I regret it? I'm not about to, but will I regret it? I'm about to meet another robot. Will I regret it? Etc. Now, we know that all correlation is not causation. Now, a lot of people think that we gave up worrying about causation in the 1960s. Did we? So should we continue to not worry about causation then? But how do you make decisions, right? Does this drug cause a cure for this disease? If it is yes, then you take it. If it's no, then you don't. Does smoking cause cancer? Yes, then you stop smoking. Right? Does hiring data scientists cause a larger profit margin? If yes, then you hire. No, if you don't. If no, you don't. So, but we need to recognize all correlation may not be causation, but some correlations are due to causation. We need to find those causes, eliminate the wrong ones we assumed in the past using new data. So this brings us to first rung of causation, which is just association or seeing. Now, 99% of machine learning and AI that you will see around you will be at this level, which is, or at least today, is at that level. You do prediction, classification, detection, recognition from images, video, speech, audio, text, tables, time series. So this is just seeing or observing. You can answer the questions like, what does a symptom tell me about a disease? Would a customer buying toothpaste also buy floss? What does a survey tell us about election results? Right? Now, so this is what? Probability of Y given X. You make an observation X, what's the probability of Y? But this limits us from reasoning about new actions, novel actions, experiments, or causal explanations. How is that? Well, let's look at this rung one. How far can we go with this? How far can we go with this? So I talked about discrimination in hiring, termination, and so forth, right? So let's talk about this one, which is monitoring of adverse impact to employees in hiring, promotions, compensation, and terminations based on gender, ethnicity, veteran status, disability, age, and so forth. Now, the interesting thing about this is, I'm going to skip a little bit of a detail here and go to the math right away. Now, the key thing, clearly this is the important need. We do not want discrimination. We do want diversity. There's a huge negative impact if you don't care for this. Now, notice the kind of data that you have. This is about hiring, right? You have locations in the first column, the type of jobs in the second column, and ethnicity of people, native Indians, 2 or more races, whites, 2 or more blacks, others, etc. So this is data from the US. Now, it talks about total number of applicants, those who are selected, those who are rejected. Now, given this data, come up with something that is going to tell me where is discrimination going on, by how much, is it statistically significant. Right? Now, we've created a system which can rank these and so forth. Now, let's go back to, I don't know, grade 8, 9, 10. We've done this before, right? What is the probability that you get a queen of hearts when you pick one card from the deck, right? What is the probability that you get a female when you pick candidates, when you hire candidates for a particular job? What is the probability that you get males when you get when you hire people for a job, right? So the way we used to calculate this is, you said, okay, what is the probability out of, so this, look at this table here. So you have males, females, hired, not hired. Numbers are A, B, C, D. Right? Total number of hired people are A plus B. Not hired people are C plus D. Male are total males, hired or not hired, meaning total applicants is A plus C. Female applicants B plus D. So to calculate the probability that this observation is by chance, what do? We say, oh, it's purely by chance. You say A plus B. choose B, which is in how many ways can you hire B females out of A plus B hired people, and how many ways can you not hire D females from C plus D not hired people, and or choose, you can say hire or choose, and how many ways can you have B plus D female applicants out of N applicants, right? And and that is equivalent. Now this is called Fisher's exact test. Just a side note on this, just to calculate this, when I joined Oracle, I was asked to do this in SQL. Now, as you will know, in SQL I can't do loops. In PL SQL I can do, of course. In SQL I can't. Now, notice that calculating factorials does require loops unless you have built-in functions. So I had to go back to Srinivas Ramanujan's lost diary, found his approximation for the gamma function, which approximates which is his approximation for the gamma function. So I found that approximation worked out amazingly in computation. N square problem reduced to 1. Now notice that I can do this. I can even do an equitable salary analysis based on years of schooling completed, business major, years with company prior to current job, years in current job, whether there are women, etc., etc., etc. Right? Now notice what questions can I not ask, or what can I not answer? Why was somebody paid less than another person? Because I didn't model the variables that are used for the appraisal, or I didn't model the fact that people are paid a certain percentage above their current salary for lateral hires. Why are certain groups hired more than others? I can say a certain group is hired more often than others, but I can't say why, right? Because I didn't account for the business process where you have employee referrals. What if I shut down the employee referral process? What will happen, right? This is a counterfactual question. Will I lose my best source of employees? How do I still ensure diversity? So I can't answer certain questions. Now, what if I'm required to have certain percentage of people in the applicant pool? Will it improve diversity? I can't answer any of those questions. So now, how do you answer further questions? Well, you can go to the second ladder of causation, which is the idea that if you do X, will you get Y? So first was you observe X and you got, do you have Y? The other one is, if you do X under Z conditions, do you get Y, right? So here you can ask more interesting questions, right? Here you are intervening in things, you are doing randomized trials, you learn by doing. So this is called causal modeling, right? Where you say that the probability of event Y equals Y, given that we intervene, set the value of X to X, while X equal to small x, while observing event Z, right? So what happens if we double the price of a product? Now, if we just double the price of product, that doesn't mean that my sales will half or double based on past data, because my current conditions are likely different. Similarly, what is the effect on prevalence of lung cancer if we ban cigarettes? Now, this question you may not believe, but it was debated very heavily among epidemiologists and statisticians from the 1950s to the 1990s. Versus if you just observe non-smokers who have the lung cancer gene. Or if I take aspirin, will my headache be cured? These questions I can ask, right? So you may say, no, I can answer all questions just by looking at the data. I see X, get Y. I see X, get Y. No, you can't. And I'll demonstrate that to you. So let's just try to make a decision with available data without counterfactuals, as we just saw. Okay. So we are all in the social distancing mode right now. Now, if the fallout to people's lives due to strict social distancing kills about 100,000 people, and coronavirus itself kills just 600 in a population of 1 billion, should I implement strict social distancing? This is the decision that the leaders of the country make. Now, you might say, well, it's a no-brainer, don't do social distancing, looking at the numbers. Now, usually at this point, I would ask for your input, but this is a webinar. It's a little tough to do that. Again, this slide for illustration purposes only, numbers are imaginary. Do not post on social media. Do not share this at all. But notice this, that if this happens, right, if there is strict social distancing and the fallout to people's lives, as people get displaced or they're not able to get food or etc., or they don't have work, So look at the numbers. Okay, so I'm going to support the first view. Now, if you have strict social distancing with 99.99% people observing the social distancing and only 0.01% people not observing it, right? Now, of the people who are observing social distancing, probably 10% of the people will experience some severe fallout, loss of job, loss of livelihood, loss of, some other problem that may occur. And even out of the people who don't do social distancing, they will also have some problems because the whole society is going through social distancing. And out of those 10% of people, 1% might even die just because of social distancing. On the other side, of the 99.99% who are doing social distancing, a very small percentage may get infected by the virus, 0.001%, let's say. Again, these are numbers for illustration only. These don't represent anything in reality, but although they correspond well to reality. And among the people who don't do social distancing at all, you get a 50% infection rate, which is well borne out by epidemiologist studies. And anybody who gets an infection, out of those, perhaps 1% will have severe enough reactions that they might die. Now, you apply this at India scale. I'm just assuming a population of 1 billion. So 999.9 million people observe social distancing, just 100,000 don't. So what happens out of these 9.9 million encounter some very, very bad fallout, like for example, the migrant workers are experiencing. And out of the 100,000 who don't do social distancing, perhaps 100 also encounter some difficulties, right? And 1% of them die, so 100,000 people die. And on the right-hand side, with the infection, we said 0.001% people from the social distancing case also get infected. So there are 10,000 people from that infected, and 50,000 from this cohort of people who did not observe social distancing. And 1% people leave, so that's 600. So the total number of deaths are 100,600, 1,600,000. Now notice that 200 times more people die due to fallout than coronavirus. Now, of course, we hope and pray that many fewer lives are affected, than due to the fallout. Now, the answer is obvious for anybody making a decision, right? That if you do strict social distancing, more people die due to the fallout than due to the virus itself. So your solution is worse than the problem. But let's just imagine that we set the social distancing to 0. Then what happens? Well, the mechanisms kind of remain the same as above, even in the no social distancing case, except that the top input changes, which is 100% no social distancing. Then what happens? Well, we have 1 billion people not doing social distancing. And out of those, 500 million will get infected and 5 million will die. So now if we look at it this way, avoiding social distancing would have cost lives of 4.8 million people. So if we know mechanisms of things, if we know how these things operate, we can make better decisions. Again, these are for illustrating the principle only, imaginary numbers. Do not post on social media, do not share this. Now, if you have signals like this from multiple sources, how do you integrate this? How do you create a system that can help you make these decisions? Should we always use mathematical or algorithmic integration, or is there a need for domain knowledge based selection and integration? We look at this example from a slightly different domain, which is investment banks. So this is at a very large investment banks, they have $4 trillion in money from very large clients, 2,000 large clients, each of whom exceeds $100 million in investment each. They have 10,000 to 100,000 end users, and it costs $20 million to replace a client. Very expensive to replace a client. So this customer asked us that, could you figure out if a customer is about to leave before they leave? When they're about to leave, you find out that's already too late. So what can we do to estimate that the client might leave? Well, number one, we need early signals, as I said, and we need to ignore misleading signals. Now, we started doing this and we realized that we didn't find any clear signals. And the reason for that was that people who manage these very large clients, $100 million, $1 billion in investment, they don't give you negative feedback so easily. They are smooth, polished enough to just say things in a gentle way. So we needed to have close to 100% recall on negative sentiment. As in, if somebody says there's a problem, we needed to pay attention to it right away. And we needed high precision. We could not be saying all clients are about to leave or 20% of the clients are about to leave, because then we'll be spend time and money chasing false positives. So here is the problem statement clearly defined, right? What is the probability of the event Y? This is written at the bottom here. Probability of the event Y, which is customer leaving or staying. Given that we intervene and set the value of X is fix the service issues, while observing competitors offering better products and there are no complaints. So what did we do? We said, you know what, give us all the data. Give us all the data you got. So what did we get? We get all the KPIs, new accounts, transfer of assets in and out, assets under management, not in good order cases, errors, all of this. Structured interaction data, emails, phone call records, service center requests, responses, phone call recordings, speech, audio, call notes, customer center call notes, activity status, firms, survey comments, all of this. Survey scores. Now, it turns out we were told that the survey scores are a golden record of customer satisfaction. Turns out this was not the case, because, surprise, surprise, people lie on surveys. And then web logs, pages visited, errors, performance issues, timeouts, activity logs, all of that. And social media, Twitter, Facebook, LinkedIn. Interestingly, for those who are large enterprises that do B2B business, although they try to get social media data, but most public social media data is not very useful, because most businesses have contracts which don't allow them to post much information about what's happening. So a lot of CIOs start off doing this, saying, let me find something on social media. Usually they'll not find it unless they are direct to customer businesses. So okay, what happened then? Well, something very interesting happened. We saw that there were a lot of complaints around about 9 months before when the customer was about to leave. Lots of phone calls, emails highlighting issues. Now, the other thing we noticed was about 3 months after that, the number of complaints went down, everything looked beautiful. The VP on the account got their bonuses, and the customer still left after 3 months. What's going on? Well, what's going on is, if your wife is complaining or if your husband is complaining, that's a good thing, because they still have hope in you, because they want you to improve. But if they stop complaining, this is the no complaints phase. If they stop complaining, that means they've given up on you. Also true for employees, with respect to employers and so forth, that it's a good thing if your customer is complaining. It's a good thing if your spouse is complaining. It's a good thing if your employee is complaining, because that means they have hope. They have hope to get things better. So we use this information that we discovered in the process and said, we are going to figure out which customer is about to leave. And here's how we did it. We said, how extreme are the KPIs and sentiment with respect to within the customer's particular segment? We found which are the key excerpts from emails, customer service notes, speech and voice analytics samples. So notice, none of the structured data gave much information. This unstructured data from natural language provided most of the information. And what we also saw is which are the locally similar cases to our customer who do much better, worse, or similar. Again, oops, Yeah, I'm going to skip this one. Right. So our results were, we used a combination of multiple KPIs, etc., and we estimated the customer tone accurately 86% of the time. Now, it was very interesting that it was used by their senior management to challenge the judgment of account managers and address the shortcomings. So, in short, the VPs lost their bonuses. But very good system, but we could not answer another level of questions. What if we had only fixed only 50% of the customer complaints because it would have cost us 70% lower? Would we still have been able to retain the customers? What if we have been fixing only 80% of the easiest problems? Would that still help us retain the customers? What if we provided better returns, still had website issues? Would the customer still leave us? As in, if we just said, okay, we'll give you just 1% higher return on your investment, and still we had some issues, would they still stay with us? We couldn't answer these questions. Now, how can you answer such questions? Then you have to come to this third ladder of causation, which is counterfactuals, where you have to create dynamic causal models or what if simulations from hypotheses. So for example, what if my flight had not been late? Was it aspirin that stopped my headache or something else? What could Gandhi have done if somebody had not killed him? What if I had not eaten too much in the last 2 years? Perhaps I would have been thinner. What if I had not smoked in the last 2 years? What's the probability that Joe's salary would be Y had he finished college, given that his actual salary is Y and he had only 2 years of college? Now notice, this question you cannot answer using standard machine learning models. Right? You have to have a causal understanding of what finishing college does to people's salaries. For example, how likely is it that Joe's swimming exercise was necessary for Joe's death, or as a sufficient cause of Joe's death? Or see, also in civil courts, a defendant is considered responsible for an injury if, but for a defendant action, it is more likely than not that the injury would not have occurred. So this is very, very important to note. Was it X that caused Y? What if I had acted differently? This is something that's not in your data. Notice, this is not in your data. How do you answer these kinds of questions? Well, these kinds of questions are answered by dynamic causal models. Now, this work goes back to my doctoral thesis, where we're talking about bacteria infecting cells. So these bacteria inject a virulent protein into the plant cell, which has a resistant protein, which leads to a signaling cascade. Now, I am not going to bore you with the biology, but notice what happens here is that certain of these cells essentially commit suicide to kill the bacteria because they release certain chemicals to kill the bacteria, such as hydrogen peroxide, and save the rest of the leaf or save the rest of the plant by committing programmed cell death. Now, what we had done for this was we created this causal diagram, right? So what you see here is salicylic acid. Salicylic acid, common name is aspirin. So looks like plants use aspirin too. So notice salicylate or salicylic acid is a negative regulator of programmed cell death, meaning if you take salicylin, your cells will not die. Okay. And then you have superoxide dismutase and gene interactions and triggering factors and superoxide and hydrogen peroxide and so forth. Now notice that the key thing to note is there are two negative feedback loops. For those of you familiar with control theory, there's one positive feedback loop, which means enhancing loop, and then there are these minor pathways. What we did was we created a hypothesis of this in the form of differential equations, actually delay differential equations for certain phenomena where we did not know the reason for the delays. So we explicitly accounted for the delays in the action of things. Now notice these equations are very, very stiff. For those of you know how to solve differential equations, you will know that there are certain differential equations which can be very stiff, as in that they don't converge quickly. So I had to write my own differential equation solver to speed this up about 150-fold. Another story. But notice, so for each of these arrows here, we wrote an equation. For each of these arrows, we wrote an equation. Now, these equations may be wrong, may be right. Initially, we just had our best hypothesis. And the idea of creating these hypotheses is that the data will prove you wrong. That's the idea. The data may prove you right, the data may prove you wrong. Through parameter sensitivity studies, we were able to figure out which of these arrows exists, which of these arrows does not exist. And we created, so actually we were able to create these results, which, you know, this is actually from our publication. So we were able to show that if you have salicylate at a certain level, you can see the program cell death. You know, if you see the first two figures, the program cell death is low where salicylate levels are high, and program cell death is high where salicylate levels are low, and where superoxide levels are high, program cell death is high, and so forth. Right? So we can do these kinds of things. This is an example of plant growth, shoot apical meristem at Caltech. But again, I'm not going to bore you with this, but the key thing to note here is that we were able to create these differential equations and able to predict very, very precisely where the next action will be. So now here is that's an academic example. Here is an industry example for predicting warranty in the semiconductor industry. All of us know everything, you know, electronics has a warranty. Now, if the part dies early, we lose money. You know, if the manufacturer has to service it, they lose money. Let's say for a laptop. So we need to do this preventive control of such processes. What do? We need to understand the process better. We need to do detection, prediction, and anticipatory control. So now this problem was very interesting and perhaps now a little bit dated in some sense, where basically what you have is these laptops get heated in absence of air conditioning, or you know, if they're operated above about 25 Celsius, they really get heated. Now, when they turn on and off, there is a coefficient of thermal expansion mismatch between different materials. So when materials expand, contract, eventually they break. When they break, and then there are issues with transistors, which I will not get into. Now, all of this requires very detailed modeling at the level of the transistors, at the level of the electrical systems, at the level of the mechanical systems, and so forth. Now, what we ended up doing was we had data coming in from different specifications from industry. The chip will not be cooled, so chip must be cooled. So you see, notice these are causal inputs, and then each of these boxes has a machine learning model running inside it. So the conclusion we get is current chip will go through larger temperature swings. Larger temperature swings cause more fatigue. These will fail at higher rates, etc. Right? Now this became a $2 billion problem actually, and it would be a breach of legal contract. So we were able to use the facts extracted from documents, statistical trends, correlations, and so forth, reasoning using inference engines, multiple source of confidence using statistical machine learning techniques, but most importantly, the physical model to be able to address the problem. So in short, we are showing that there is a need for dynamic causal models in the enterprise, perhaps together with data-driven models, going from the level of association, which is the leaf level models, to the level of intervention, where I'm able to say, if we do X, what happens? And counterfactuals, where we say, if we did not do X, what would happen? Thank you very much for your time. We are open for questions. I'll be happy to go back to any slide if you